I would like to start by thanking all the organizers for the opportunity of having me here, even if we haven't had the occasion to meet in person with some of you. But I hope we will find the time in the future. Okay, so I will start by, let's say, saying a few words about the motivation of this research. This is a research that I've been conducting with my former advisor, Professor Flandoli, and with Dejun Luo. And basically, the aim is that of find alternative ways of computing certain quantities like probabilities associated to some SPDEs, so to some stochastic PDEs. Let's say that the final target would be to be able to treat stochastic PDE of fluid dynamical type, like here I just wrote the stochastic Navier-Stokes equation. That would be our final goal. Even if, let's say, at the present time, we are not yet able to reach such kind of complexity for equation, but more on that you'll see later. But still, since some of the results are quite promising, it is still worth to let's say, keep trying on this research. Okay. I will start by an SPDE, a general SPDE with additive noise in abstract form. So let's say here this equation lives in an Hilbert space H. W is a cylindrical Brownian motion in H, which means that it is independent in all the directions. A is a linear operator, which has the usual assumption of being self-adjoint and negative eigenvalues. The same holds for Q, but with positive eigenvalues. And there is a nonlinearity B in a general form. Of course, this is an abstract form, but what you can imagine is that this is a stochastic equation where A can represent the Laplacian and B is the nonlinearity that you want to treat in your model. Okay, so about the nonlinearity, B, in a sense, this is less usual as an assumption because we assumed the nonlinearity B to be bounded. So in a sense, it's only bounded measurable. So let's say we don't assume any regularity, but we still need it to be bounded. It is a strict assumption because you can see is very far from the nonlinearities of fluid dynamic type, like those of Navier-Stokes equation, which are quadratic. So we still are not there. And basically, what we would like to do, we take this equation in this general form, and what we would like is to find ways to compute probabilities related to this SPDE. Let's say classical methods, the most basic one is, let's say, classical Monte Carlo, let's say, which basically means take independent realizations of the noise. So take independent realization of this process X. And what you do is, if you want to compute the probability that your equation lies in a certain set, what you have to do is simply take arithmetic averages over independent samples. This is, of course, very, very old, very classical. It is very simple. It has its downsides. For example, it is not very accurate, especially when one has to deal with extreme events, even if there are variants which are specific for that purpose, which I will not discuss here. And also, it is, in a sense, very expensive because one has to simulate this. You have to imagine this is a PDE with noise, so you have to simulate this PDE many, many times to produce independent samples. And also, it's expensive in the sense that if you want to, let's say, change some of the parameters, what you have to do is basically do everything again from the beginning. Let's say that, for example, you want to change your small x that here represents your initial condition. Then you have to do everything back again. And why you would like, for example, to change your initial condition? Let's say that you are studying some model for climate or for whatever, and you have some uncertainty on your initial data. And so perhaps what you want to do is to change it and do some randomization of the initial condition in order to see what are the effects. And with the classical methods, let's say, you cannot. So what we would like to do is basically he used the tool of Kolmogorov equation to find alternative ways to computing such probabilities. I have to say, in this, let's say, area which is numerical for SPDEs, but let's say for high-dimensional PDEs, there are of course many works. I will just mention some of them which has some similarities with what we did. One is from Chen and Maida, which studied the Fokker-Planck equation. We studied the Kolmogorov equation, but you know that there are relations. Which basically they studied with try to approximate the Fokker-Planck equation of a nonlinear process by using a convex combination of Gaussian distributions. While there is also another series, many works of Jensen and many co-authors, which try to do the same, let's say, tackle the same problems for finance, and they use machine learning, where basically what they did is try to let's say run a few samples in order to make their network learn the problem, and then they are able to change some, for example, the initial condition and reproduce the results since they have already trained their neural network. But in our case, what we're doing is slightly different, even if there are some similarities. First, we are trying to study the Kolmogorov equation associated with SPDE that I brought with this SPDE. So the Kolmogorov equation, just briefly, is an equation for expected values related to this process xxt. Basically, what you do, you take an observable u0 that could be, for example, the indicator function of certain set, and then this function here, ut and x, you can show that satisfies this equation, which is the Kolmogorov equation in infinite dimension in this case. It's worth noting that usually the Kolmogorov equation is written in backward form, so it as a backward PDE, but here, since we choose every coefficient to be time independent, of course, you can do a reverse of time and rewrite everything in a forward form. So what is the interest in this equation? Well, for example, it is clear that if what you want to compute are probabilities related to this process xt, then since u is an equation for expected values, the probability that you want to compute is simply the solution at time capital T, if capital T is the time where you want to compute probabilities. And so let's say if one managed to compute solution to the Kolmogorov equation, it would solve the problem of computing these probabilities. Of course, the problem is not so easy. So I mean, it's not so easy to solve this kind of this equation in high dimensions, and so it requires specific techniques. In our case, what we did is start to rewrite everything. So the Kolmogorov equation associated with x in a perturbative form by using the semigroup associated with the linear part of the SDE. So what we did is basically you consider an equation for the variable zxt, which is basically the same as for x, but it has any nonlinearity. The nonlinearity is not here, it's not present. So this is a linear problem. And what you do, you can consider the semi-group associated to it, which acts on test function phi by taking expected values of phi computed in zxt. And using this semi-group, you can write the original Kolmogorov equation of the nonlinear process, so B is here, in a perturbative form. And let's say from the point of view of numeric, once you have an equation which is in a semi-explicit form, like in this one, what you would like to do is to apply a fixed point, basically. So you start an initial profile for your solution, and then you start iterating this map until you reach convergence and you are close to the real solution. However, here the situation is not, let's say, is not so simple, because on the right-hand side here, due to the structure of the Kolmogorov equation, it appears a derivative of the function u. And so as it is now, you see, you cannot really apply a fixed point immediately, because on the right-hand side, you don't have u, but it's derivative in infinite dimension, so it's differential, let's say. And so if one wants to apply a fixed point to this equation, what you have to do, you have to make the semi-group associated with the linear part has to absorb the differential in front of the variable u. If you manage to do so, then you can try to do a Picard iteration on this map. And so about this semi-group associated with the linear part, I will need to recall some basic notation. Oh, sorry. Okay. Okay, this is, I'm recalling the notation. So remember, A is self-adjoint with negative eigenvalues and Q is positive. Then what you can do is define the stochastic convolution, which is this process WA and between S and T, which is the convolution, the stochastic convolution of the semi-group generated by A. This is, let's say, a process with covariance operator Qt minus S, which can be expressed in this way. And basically, what you can do is you can compute derivative of this semi-group along the direction h, and without involving any derivative of the function of your test function phi. This expression that you see here involves various ingredients. One of those is this operator lambda t, which is the composition between the covariance operator to the power -1/2 and the semi-group generated by A. And the other one is the stochastic convolution, which is rescaled by the covariance operator with the power -1/2. And above this, I just want to mention that this expression for the differential of the semi-group has some difficulties related to it. Let's say a nice property is that you can control the norm of the differential by the norm of this operator lambda t. However, this operator lambda t, as you can see, has a norm that is singular at t equals 0, and that is, of course, you can understand it. Let's say, looking roughly at this expression, there is this Qt -1/2, which is singular, but the operator A, the semi-group associated with the operator A, regularize this operator lambda t, but at t equals 0, this operator gets to be the identity, so there is no more regularization, and you can, in few words, understand why there is a singularity. However, if you recall that what we want to do is to perform a fixed point, you realize that this singularity, at least in this case, which is the case associated with cylindrical linear process, is not bad, because this power 1/t1/2 is integrable in time. And so we will be able really to perform our Picard iteration. And so now that we understood how to to make sense of this expression without taking differentials of u, what you can do is really do a Picard iteration on this map. And the initial, let's say, you have to choose an initial distribution u, an initial solution u, and that is basically the solution associated with the linear process. So the linear process zxt, which is u0. We'll call u0. And okay, there is some rewritings that you can do. Basically, if instead of considering un and its successive iterates, you consider increments, you can express the final solution as a sum instead of a limit, and the advantage is that the initial condition disappear in the iteration. But this is just for convenience. It's the same way you can do it with u. Okay, so now I will say something about all these expressions. We won't give any proof for a matter of time because they are quite long. But basically, here I've wrote an expression for the first term of these approximants for the solution of the Kolmogorov equation V1, and of course it involves the operator lambda and the covariance operator Qt. But a nice thing about it is that all it involves, since it's based on the semi-group associated to the linear part, it involves expected values which are based only on the linear process ZXT. So in a sense, you can already imagine that the advantage of this method would be that to compute your UTX, so the solution of the Kolmogorov for the nonlinear process, what you will have to do is basically take averages of ensembles of only linear processes. And of course, you will have to do manipulation. Of course, the nonlinearity has to appear somewhere, otherwise there is no link between the linear and nonlinear process, but that's the idea. And here, let's say before I wrote only the first term of this expansion because it's the easier one to understand. Here, just for completeness, I wrote all of those. So the general term Vn can be expressed as a series of n time integrals of an expression, which of course still depends on the operator lambda, the covariance matrix Q, and the nonlinear operator B. But it's a bit less easy to understand, but the general structure, let's say, is the same. It also makes sense that it is in a series of n time integrals, since it is the nth order approximation of a Picard iteration. And what we were able to prove together with Flandoli and Dejunluo is that if B is effectively of this form, so it's bounded between H and H, then this series converge uniformly with its derivative to the unique solution of the Kolmogorov equation. And moreover, there is an estimate on how fast this Vn goes to 0, so how fast your series is converging to the solution that you are interested in. By the way, by this expression, you can see that the convergence is more than exponential, so it's actually quite good. Okay, so moving on how you apply concretely this method. Let's say there are the following two steps. What you want, since as I said, all the method is based on taking averages and computing values related to the linear process instead of the nonlinear one. So what you want to do is basically store a huge number of trajectories, of independent trajectory of this process Z. By the way, you can simulate, for example, this process with whatever you want, for example, with Euler's scheme, starting with initial condition 0. And since the problem is linear, you can compute the solution, which starts from X, that is what you need, by the solution starting from 0 with a term that depends on the initial condition. Of course, this is only one of the advantages is that you can change the initial condition easily because you simulate the process starting from 0 and then change X very easily. But you can do the same thing for different values of, let's say, here I wrote sigma, I forgot to write before, meaning if you want to change the amplitude of the noise, if you want to study the zero noise limit of your system, that you can do quite easily, because in this problem, let's say that you want to compute the solution where instead of a square root of Q, you have a sigma in front, you basically just need to add a sigma in front of here, and that works. So it's another feature that it's good because it makes you very fast to change some of the parameters of your problem. Of course, what I said is really only one of the strategies that are possible. I said, okay, you can simulate this linear equation. But of course, this linear equation is as a Gaussian distribution, since it's linear. So there could be several approaches to obtain samples from this process, since it's Gaussian and the covariance is given, it's known. So there could be many options. And okay, once you have, let's say, stored and computed many samples independent realization of this ZX, what you have to do is simply to compute all the subsequent iteration Vn in order to approximate the solution to your Kolmogorov equation. And so, of course, this has to change. Every time that you want to study a problem with a different nonlinearity B, you have to change, you have to redo this second part. But in a sense, this second part, I will show you afterwards some plots of the timing is faster, since you don't have to solve any equation that involves noise. You already have all the ingredients. What you have to do is simply to compute some integrals and take expected values. Of course, the method is iterative, so there is, okay, you can have an estimate by the theorem on when you should stop, but you can see this as an iterative method, so you stop when approximants gets below a certain threshold. And that's it. So advantages, let's say, apart that you don't have to resimulate this Z, just to summarize, is that this simulation of the linear process you do only once, and then if you want to change some of the parameters, you can do as whatever you want. It's faster. Okay, and so now we move on to some of the results. I will show you only very simple result. As I said before, the present theory doesn't allow us to go are ready to fluid dynamics problems. So we took very easy examples. So what we did is basically simulate an SPDE on dimension 1 on the torus. And you take as a matrix Q the identity matrix. A12 mimics the Laplacian operator. So you take A diagonal with components equals to minus k squared. And you take an observable U0, which is the one associated with Kolmogorov equation. So basically we are computing probabilities that our nonlinear process lies in this ball of center 0 and radius 1. And we take a very simple nonlinearity, which is basically the sinus. So it's bounded, it satisfies the hypothesis, but this is also smooth. And what you see here, there are two plots. Let's say I will describe briefly. The one on the left is the trajectory of the Kolmogorov equation for a fixed x. So for a fixed initial condition of the stochastic PDEs, but for various time ranging between 0 and 1. And here you see various lines. Let's say the blue one is a reference solution that we computed by classical methods with high accuracy in order to have something to compare to. And the yellow line that you show here is the solution obtained at a certain iteration, a certain number of terms that we add. Here it is the 6th. On the right-hand side, you see basically the error. There are the absolute error, which is the error with respect to the reference solution, and there is the iterative error, which is nothing else that the difference between two consecutive iterates. And as you can see, this is a plot in log scale. The iteration, the error of the iteration goes to 0 exponentially fast as one expected. And as I was mentioning, here I will show you a plot of the time of computation. Basically in the same setup as we did before. What we did is we did simulations by changing the amplitude of the noise. So imagine in front of your matrix Q, in front of the linear process, you put a coefficient sigma and you change it between 1 and 0.1. We did 10 trials, and we measure time. We measure the time that we need to have to compute, let's say, the time, compute the solution n times. So for example, the blue one, which is the reference case, represents the time that you have to spend to compute the solution in value 1, 0.9, 0.8, and 0.7. So it's increasing because it's a sort of cumulative time. Of course, this is aligned because classical methods it doesn't matter how is the value sigma in influencing the time of computation. And let's say the yellow line and the red line are those associated with the iteration scheme that I presented. Basically, the yellow line is the time that it took to compute the solution with sigma equal 1, 0.9, 0.8, 0.7, etc., with our iteration scheme, including the time of doing the simulation of the linear process only once. So this is why it's iteration scheme plus ZT. The red one is only the time that it takes to compute iterations, but let's say that at least once you want to compute your linear process since you need it. But then you can reuse it for, this is the point, you can reuse it for different values of sigma. And this is where you see the advantages. Since you do the simulation of the linear process only once, the saving in time for testing various parameters is quite big. However, the method, it's good only if it works in sufficient number of examples. So what we did is basically we tried some other examples which are less easy. The nonlinearity, that the same setup as before, but we choose a different nonlinearity, which makes the problem more difficult. And we took something which is, let's say, is sort of cubic, since the numerator is sort of cubic. Y bar is a fixed element of our Hilbert space. And then it is normalized in order to be bounded so that it satisfies the hypothesis of the theory. And what you see is that the result is not satisfying at all. In fact, your reference solution, let's say, is the blue one and the yellow one doesn't. Okay, you can see it from the plot of the error, but you can see it also from the trajectory. It's really not satisfying. And so we started to ask ourselves, why was it, since all the hypotheses are here, there'd be something going on that we haven't understood yet. And so here we decided to went with a change of perspective on the problem. So as I mentioned before, as we wrote before, what we are doing is approximating the solution of our Kolmogorov equation as a series of these Vn of these terms. However, if you look at those of this Vn of this complete expression, what you see is that all of those have in common this U0, which is the observable that you are looking around computing in the linear process. And so what you can do is that you can incorporate U0 from this big expression, since it does depend only on small t, which is not involved in the time integration, and put it outside. And what you get, hence, is that what you left, you call it In, and on this sum, what you can do is sum inside the expected values. And what you get is, hence, that you are computing the solution of the Kolmogorov equation associated to a process, a nonlinear process X, as expected values of the same observable computed in a Gaussian process, but which is corrected by this rho n, which is sum of all the terms that are experienced. And so what you're doing is basically taking, if you take averages as arithmetic averages, you're basically taking the same averages as before, but on the Gaussian process, and we are giving different weight, let's say, to each of the sample, depending on what's the values of this series of integrals. And so I made some plots just to visualize the problem. This is a two-dimensional plot. Of course, what we since we discretized our problem on Fourier, we took many Fourier components, and so it's not possible to visualize. So this is only a two-dimensional projections of the samples that we obtain in terms of Fourier components. And the blue, let's say the blue ball is sort of samples from the nonlinear process that we want to approximate. And the red one are sampled from the Gaussian process. And of course, they are not equal because the problems there are different. Let's say for visualizing, I also made one-dimensional plots, so histograms, which are easier. And what we are doing is basically taking the blue histograms, which is the distribution of one of the components of the nonlinear process, taking the red one, which is the Gaussian, the one of the Gaussian process ZX, and we are giving different weights to each of the samples of these Gaussian samples. And what you obtain is something that I drew here in yellow, which of course it's better, as you can see, than the Gaussian, because of course the Gaussian is not a good approximation, but it's not perfect. Especially it has some great disadvantages. For example, here you can see the Gaussian does not cover the entire support of the nonlinear process that you want to approximate, so the blue one. And so even if you give different weights to each of the samples, you won't never be able to recover this distribution fully. In fact, this tail is completely uncovered. And so one thinks perhaps the problem is that our initial approximation via Gaussian is not good enough. And in this sense, what has been a nice way to solve the problem is to basically improve the initial approximation of the Gaussian process. I'm thinking I'm going a bit long in time, so I will make it short. Basically, what you can do is
you have you have 5 minutes.
Yeah. In fact, I will try to make it short.
Thank you.
Thank you. So basically, what we did is move the mean of our Gaussian process ZX by adding and subtracting a deterministic function in order to make it more close to the nonlinear process X that we want to approximate. And here we can speak on how to do it, but basically what we did is simulate one deterministic problem. Basically, this is only a PDE, which is the same structure of the initial SPDE, but without noise. And so we try to get close with our Gaussian distribution to the solution of this deterministic problem. And if you do so, what you see is that if your initial distribution, let's say, was on this shape, this is the same picture as before, once you move everything in order to be closer, it gets like this. And of course, they are not yet perfect, but as you can see before, the Gaussian was the red one compared to the blue one, and now it's much more close already. And so when you start to perform your iteration given by the Picard iteration associated with Kolmogorov, what you get is that since you started much closer, the final approximation will be much better. In fact, as you can see here, for example, the tail that before was left out and was not at all approximated gets much better. And in particular, in the case before, in the same case before, if we apply this strategy and compute iterations, et cetera, the results that you get are much better. And so, in a sense, once you say, okay, now I solved also this problem, you can try to do something else. And also, what we did is this was just an experiment. We went outside of the present theory of our present theory, which requires B to be bounded, and took something which is not. So this is the same nonlinearity as before, which is cubic, but is not. Sorry, there should be some k's around here just to mention the k component. So this is not in our present theory, but still, we tried it out and it works nice. But this is only, okay, you can say, okay, this is a nonlinearity, but it's very easy because in a sense, it acts on Fourier components. Each Fourier component depends only on the corresponding Fourier components. So it's kind of an easy problem. And as I said before, what we wanted to do in the end was move in the direction of stochastic Navier-Stokes or problems related to fluid dynamics. And so let's say instead of taking, sorry, spoiler, instead of taking the real Navier-Stokes equation, which is more complicated, what we did is take, let's say, a sort of simplified model for the Fourier modes of the Navier-Stokes equation. This is called the dyadic model of turbulence. And basically, what it mimics is the behavior of the Fourier components of Navier-Stokes. It has some nice, let's say, it has some similarities like conservation of energy, cascade of energy, et cetera, but okay, I won't go in many detail of this problem, but we took a nonlinearity which mimics this effect on Fourier components, and what you obtain is this one. So same plot as before. The distribution that we want to approximate, so the one of the nonlinear process is the blue one, and our Gaussian is the red one. Of course, you can apply the same strategy that we did before. So try to move your Gaussian in order to be closer to what you want to approximate via Picard iteration. And okay, it's a bit better, but still, perhaps it's too far as a starting point. You can imagine that if you try to compute probabilities related to this most left-hand side tail of this blue boomerang that you can see, there's no way that the approximation would be good. There are no samples of the Gaussian over here. And so this is, in a sense, the end of the talk and the progress that we made. There are certain examples that we understood are not yet, we haven't understood yet how to treat. For example, one of those is that of the dyadic model of turbulence that I showed before, where the approximation of the Gaussian, I didn't even show you any plot about the Kolmogorov equation because they are very bad, so they're meaningless. So that will be the main point. Other point, of course, is to extend the theory, because if you want to perhaps understand better the problem, you cannot go by tries and the numerics. You have to have a robust theory, and our present theory only allows us to go to B bounded, even if some recent progress still by us allow us to take B of strictly sublinear growth, so not linear, strictly below. So it's a bit of an improvement with respect to what we had before of bounded, but it's not yet quadratic, which is, let's say, fluid dynamics that we would like to treat. Also, other problems related, open problems, is to, if possible, learn how to use information on conserved quantities, because at present the theory doesn't use anything like conservation of energy or stuff like that we know are very important when one wants to try difficult problem like fluid dynamics. And also, finally, as I said before, in this case we had the cylindrical linear process, which in a sense is the more canonical one. It would be nice to have to study degenerate noise, so where there is no noise on some of the direction, or also multiplicative or transport noise. And okay, that's the end of my talk. Thank you.